We'll start in 1 minute. We'll continue with the final exam review. The final exam is over everything. And a reminder, the final exam will be on Monday, May 3rd from 10 a.m. to 12 p.m. We'll continue working on this problem that we started yesterday. We have a parametric curve defined by the equations x equals t plus 2 and y equals t to the second minus 2t. So in the next part, find the area below the curve and above the x-axis for values of t from 2 to 3. So the form that the integral takes from alpha to beta is g of t times f prime of t dt. So for t values from 2 to 3, we have the definite integral from 2 to 3. G of t is just what y is equal to. So a reminder that y is equal to g of t and x is equal to f of t. So we put in what y is, or g of t, t to the second minus 2t. And then since x is just t plus 2, dx dt, or f prime of t, is just 1. So times 1 dt. And then we have a simple integral to evaluate. We have t to the third over 3 minus t to the second from 2 to 3. So 3 to the third over 3 minus 3 to the second, and then minus the quantity 2 to the third over 3 minus 2 to the second. So on the left, 3 to the third is 27 over 3 is 9. 9 minus 9 is 0. So we have 0 minus 8 thirds minus 4. So 4 is the same as 12 thirds. So we end up with the negative of negative 4 thirds or 4 thirds for the area. In the next part, using the same parametric curve, we set up an integral for the length of the curve on the interval from -1 to 3 for the t-values. The formula for arc length for parametric curves. We have a definite integral, we'll say from alpha to beta, and then inside a square root we have dx dt squared plus dy dt squared dt. All right, in this problem, x is t plus 2 and y is t to the second minus 2t. So dx dt is just 1, dy dt is 2t minus 2. So we're just setting up the integral, so let's just write the integral, the length, the arc length is from t equals -1 to 3. And then inside the square root, we have 1 to the second plus the quantity 2t minus 2 to the second. So that's good enough for our purposes, setting up the integral. Okay, on the next page, we have a polar curve. We'll graph the polar curve, r equals sine of 2 theta. Then we'll find the area of one loop. And then thirdly, we will set up an integral for the arc length of one loop. So a good strategy in general when graphing polar curves is to first graph the Cartesian coordinate graph, or the rectangular coordinates. So the Cartesian graph so since we have r equals sine of 2 theta, so up here I'll just do a little bit of arithmetic. 2 theta, so if we write 0 less than or equal to 2 theta, which is less than or equal to 2 pi, and then solve this compound inequality for theta, that will tell us what the length of an interval for one complete cycle is. So divide each of the 3 parts by 2, and we get 0 less than or equal to theta, which is less than or equal to pi. So in other words, from 0 to pi, we'll get one period or one cycle of the sine function. And then between pi and 2 pi, we'll get another cycle. So if we subdivide the interval from 0 to pi into 4 subintervals of equal length, then we'll go from 0 to pi over 4, and then to pi over 2, and 3 pi over 4 to pi, and then the interval from pi to 2 pi, subdivide that into 4 intervals, subintervals of equal length. So this one is 5 pi over 4, then 3 pi over 2, 7 pi over 4. Okay, when theta is 0, sine of 0 is 0. When theta is pi over 4, 2 times pi over 4 is pi over 2, and sine of pi over 2 is 1. Then when theta is pi over 2, 2 times pi over 2 is pi, sine of pi is 0. So this will give us the first loop in the polar curve. And we know what's going to happen after that. The graph will do this between pi over 2 and pi. And then between pi and 3 pi over 2, we'll get the first half of the second cycle. And then between 3 pi over 2 and 2 pi, we get the second half of the second cycle. Okay, so this is the rectangular coordinate graph, or the Cartesian graph. And then we can use it to help us graph the polar curve. So with dashed lines that correspond to multiples of pi over 4. So this one is 3 pi over 4. This one down here is 5 pi over 4. And then 7 pi over 4. Okay, so the polar curve at theta equals 0, the value of r is 0. By the time we get to pi over 4, the r value is positive 1. So we have the first half of the first loop. So this is a radius of 1. And then from pi over 4 to pi over 2, we go back to 0. From pi over 2 to 3 pi over 4, the r values are negative. And so in the opposite quadrant, we draw the polar curve. And then from 3 pi over 4 to pi, the negative r values go to 0. So the loop goes back to 0. And then from pi to 5 pi over 4, the r values are positive. So they go to positive 1 at 5 pi over 4. And by the time we get to 3 pi over 2, the r value is 0 again. And then just one more loop between 3 pi over 2 and 2 pi, the r values are negative. So the polar curve will be in the opposite quadrant over here. Okay, so each one of those loops is supposed to look like each of the other three. But my picture doesn't quite look like that. Okay, then in the second part, find the area of one loop. So the area enclosed by a polar curve, the formula for that, if we have a definite integral, say from alpha to beta, and then it's 1/2 r squared d theta. Where r is the function of theta. Okay, so that's the formula for the area of a polar curve. So we want to find the area enclosed by one loop. So if we pick the first loop occurs between theta equals 0 and pi over 2. So for this particular case, the definite integral from 0 to pi over 2, and then 1/2 r squared, this is 1/2 times sine of 2 theta squared. Okay, so we'll use an identity for sine of 2 theta squared. We'll continue that down here. So we have this constant 1/2. We'll bring that out front. And then we'll replace sine of 2 theta squared with 1/2 minus 1/2 times cosine of 4 theta. And then we can evaluate this integral. For convenience, I'm going to first factor 1/2 out and bring that out and multiply that by 1/2. So we have 1/4 times the definite integral from 0 to pi over 2 of 1 minus cosine of 4 theta. And then we can evaluate the integral. An antiderivative of 1 with respect to theta is theta. And then an antiderivative of negative cosine of 4 theta with respect to theta is negative 1/4 times sine of 4 theta. And then we evaluate this between theta equals 0 and pi over 2. So we get 1/4 times the quantity. When theta is pi over 2, we get pi over 2. And then minus 1/4 times sine of 4 times pi over 2 is sine of 2 pi. And then subtract the quantity 0 when theta is 0, and then minus 1/4 times sine of 0. So the only thing that isn't 0 is pi over 2. So the area enclosed by one loop is pi over 8 square units. Okay, the third part, set up an integral for the arc length of one loop. So for a polar curve, the arc length formula is defined as a definite integral, we'll say from alpha to beta, and then we have the square root of r squared plus the derivative of r with respect to theta squared d theta. So we're just setting this up, but I'll remind you of what what r is. R is sine of 2 theta. And then the derivative of r with respect to theta is 2 times cosine of 2 theta. And one loop occurs between 0 and pi over 2. So the arc length of one of those loops is the definite integral from 0 to pi over 2 of the square root of r squared, which is sine of 2 theta squared, plus dr d theta squared. So when we square 2 times cosine of theta, we just get 4 times cosine of 2 theta squared. And so that's the answer we get if we're just setting up the integral for the arc length of one loop. Okay, the next page, starting with the chapter 11 material. So the first one, does the series converge or diverge? So when you see this one, the series, the terms are e to the 1 over n minus e to the 1 over n plus 1 as n goes from 1 to infinity. So what comes to mind when you see that? Or if it doesn't immediately come to mind when you start to write out a few terms, then something might come to mind. So this is going to be turns out to be a telescoping series. So we'll write out a few terms. We start at n equals 1. So when n is 1, we get e to the 1 over 1, or just e to the first, and then minus e to the 1 over 1 plus 1, or 1 e to the 1 half. So this occurs when n equals 1. Then we add that to the second term in the series when n is 2. So when n is 2, we get e to the 1 over 2, and then minus e to the 1 over 3. Whoops, 1 over 3. This is the term that we get when n is 2. So we add that to, we'll just do a couple more. When n is 3, we get e to the 1 over 3 minus e to the 1 over 4. This is when n equals 3. Okay, then the nth term. So in other words, when n is n, we get e to the 1 over n minus e to the 1 over n plus 1. So all of those together give us the a term in the sequence of partial sums that we traditionally use S sub n to represent. And you can see that the only survivors are the very first term, e to the first, and the very last term minus e to the 1 over n. So I'll point out the obvious, minus e to the 1/2 plus e to the 1/2, those add up to 0. And then minus e to the 1/3 plus e to the 1/3, those add up to 0, and so on and so on. So the nth term in the sequence of partial sums, S sub n, is e minus e to the 1 over n plus 1. And then if the limit as n goes to infinity is a finite number, then that limit is what the series converges to. So does the limit of S sub n equal a finite number? So what's the limit of e minus e to the 1 over n plus 1 as n goes to infinity? The number e is unaffected by n. And as n goes to infinity, the exponent 1 over n plus 1 goes to 0. And e to the 0 is 1. So the limit is e minus 1. So that's the limit of the sequence of partial sums, which is a finite number. So that means the series converges to e minus 1. So that series converges to e minus 1. Okay, the next example, does the series converge or diverge? This time we have terms 2 to the n plus 4 to the n over e to the n. So what do you think? Does this series converge or diverge? And how can you show it one way or the other? Well, we could rewrite this series since there's just one denominator or one term in the denominator. We can write the terms in the series as a sum of two terms. And 2 to the n over e to the n, that's the same as 2 over e in parentheses to the n, and then plus 4 to the n over e to the n, that's the same as 4 over e to the n. If this series converges, since we're adding the terms, then that would be the sum of two individual series that converge. So what do you think? So we could think of this as a sum of two different geometric series. Since 4 is greater than e, the series of 4 over e to the n diverges. And since we're just adding positive numbers to that, it has to diverge. Okay, another option, use the test for divergence. If we take the limit of the sequence, 2 to the n plus 4 to the n over e to the n, we can see that this does not equal 0. So in particular, the limit of 4 over e to the n does not equal 0. The number 4 over e is greater than 1, and when you raise a number 1 to increasing powers, the number only gets bigger. So this limit is actually infinity. So according to the test for divergence, the series diverges because the limit of the sequence does not equal 0. Yeah, the next example, we have the series with the variable x in it. The terms are x plus 2 to the n. So for which values of x does the series converge? So what are we looking at? What kind of series is it? It's a geometric series. So we have a quantity raised to the power n as n goes from 1 to infinity. So in order for this to converge, the common ratio, or the absolute value of x plus 2, must be less than 1. So this inequality, the absolute value of x plus 2 less than 1, without the absolute values, this means negative 1 is less than x plus 2, which is less than 1. And then subtract 2 from all three parts, we get negative 3 less than x less than negative 1. So it converges for those values of x. Okay, the next two examples are just short answers. Starting with the one on the left. The terms in this series are 1 over n to the 2/3, and n goes from 1 to infinity. So does this converge or diverge? And how do we know? So I'll wait a few seconds and let you answer. Okay, we got an answer. This is a p-series P series, the value of P is 2/3. And whenever the P value is less than or equal to 1, but if it's less than 1, it diverges. So in general, for a P series, if the terms are 1 over n to the P, then it diverges if the P values are less than or equal to 1, and it converges when the P values are greater than 1. Okay, so the next one is also a P series. And this P value is 3/2, which is greater than 1. So we can say that this one converges. All right, moving on to the next page. Determine if each series converges or diverges, indicate which convergence test is used, and include appropriate computations. So this one, the terms are -1 to the n over 5n minus 3, as n goes from 1 to infinity. So this is an alternating series. So if we use the alternating series test, there are two conditions to check. So just a note, I recall on the last test, some misunderstandings. So if you have an alternating series, where you have -1 to the n and then b sub n, the b sub n is greater than 0. And then when you're using the alternating series test, you check to see that the limit of the positive terms is 0, and also check to see that the sequence of those positive terms is decreasing. So those are the two conditions. So in this case, b sub n is +1 over 5n minus 3. So the limit as n approaches infinity of 1 over 5n minus 3, the denominator goes to infinity, so the limit is 0. So that's one of the conditions. The b sub n plus first term looks like 1 over 5 times n plus 1 minus 3. Do a little bit of arithmetic. We get 1 over 5n plus 2. Compared to the nth term, 1 over 5n minus 3, how can we include appropriate computations to show that b sub n plus 1 is less than or equal to b sub n? Okay, one way to do it We can acknowledge that 5n plus 2 is greater than 5n minus 3, as long as n is a positive integer. We all agree with that. So if 5n plus 2 is greater than 5n minus 3, then the reciprocal of 5n plus 2 is less than the reciprocal of 5n minus 3. So this is sufficient to conclude that the n plus first term is less than the nth term. So this series converges by the alternating series test. Okay, the next example. In this series, the terms are the nth root of n divided by n. So what convergence test do you want to use this time? So I suggest the limit comparison test. If it doesn't work, we can try something else. So what series do I pick to compare it to? That's another question. So a couple of things stand out. I know that the limit of the nth root of n is equal to 1. And in the denominator, we just have an n. So I'm going to compare this with the harmonic series. Which we know is divergent. So in the limit comparison test, if we compute the limit of the ratio of terms from the sequences, so the nth root of n over n divided by 1 over n, if this limit is equal to a finite positive number, then that means both series either converge or both series diverge. So when we simplify this complex rational expression, we get the nth root of n over n and then times n over 1. One factor of n cancels from the numerator with the denominator, so we get the limit of the nth root of n. And we've seen a couple of times this semester that the limit of the nth root of n is equal to 1. So that's a finite positive number. So by the limit comparison test, the original series diverges because the series that we compared it to also diverges. All right, the next example, the terms in this series are 3 to the n times n to the second divided by n factorial. So any particular test you want to use? I might not pick the one that you want, but what one would you use? Okay, I got a suggestion of ratio. That's the one that I lean strongly towards. So ratio test. Okay, so the limit of the n plus first term divided by the nth term in absolute value. Everything is positive. I'll go ahead and put the absolute values around it anyway. So we have 3 to the n plus 1 times n plus 1 squared over n plus 1 factorial divided by the nth term, which is 3 to the n times n to the second over n factorial. So in the next step, we'll simplify the complex rational expression, and we can get rid of the absolute values. So we'll get 3 to the n plus 1 times n plus 1 squared over n plus 1 factorial, and then multiplied by n factorial over 3 to the n times n to the second. So I'm going to write well, 3 to the n plus 1 over 3 to the n simplifies to 3, a factor of 3 in the numerator. And I'll go ahead and write some of the other stuff. So n plus 1 squared times n factorial. Instead of n plus 1 factorial, I'll write that as n plus 1 times n factorial. And then we still have an n to the second. Another cancellation, n factorial divided by n factorial cancels. And over here in the numerator, we have n plus 1 squared, and in the denominator, we have n plus 1. So we have a single factor of n plus 1 after the cancellation. And then in the denominator, we have n to the second. So by now, we probably know what the limit is, but let's take it out a step or two more. In the numerator, we have 3n plus 3 over n to the second. So this limit will be 0. The denominator outpaces the numerator. So this limit is 0. And since 0 is less than 1, the series converges by the ratio test. Hey, we can get started on the next one. In this next series, the terms are negative 2n over n plus 1 to the 5n. So here's a chance to use the root test. So the limit as n approaches infinity of the nth root of the absolute value of negative 2n over n plus 1 to the 5n. And so when we take the nth root and the absolute value, we'll just be left with 2n over n plus 1 to the 5th. But we can move the limit to the inside of the parentheses, and the limit of 2n over n plus 1 is 2. So this limit is equal to 2 to the 5th, or 32. And 32 is greater than 1, so this series diverges. Okay, that's all we have time for today. We'll do more reviewing on Friday. Go ahead and sign in for attendance.